All right, before we tackle this question, this lesson is all about area approximations. Before we tackle this question, can you do this for me? The answer is not 4. It's funny. It takes 1 unit for students to forget the fundamental theorem of calculus. When I introduced to you the fundamental theorem of calculus, we talked about how displacement, distance, could be calculated either by doing velocities times times. Velocity times time is the area under a velocity curve. Area under a velocity curve, right? What was the other way that we could have calculated distance, or mostly displacement? What was the other way we could calculate displacement besides area under a velocity curve? Ending position minus a beginning position. Now, what was the connection between velocity and position? What? The antiderivative, integral, antiderivative, antiderivative. Remember this step? Everybody forgets this step because once you start using your calculator, you think all you do is start plugging in values. But nope, not true. Remember, you can take the antiderivative. You don't need the plus c because when you subtract these values, the c's will go away. We don't care about, it should be 8/3. We don't care about like our starting position. We just care about really an initial position. We just care about a starting position and an ending position. This is like velocity. This is position. This is my ending position. This is my starting position. 8/3 is the answer, not 4, right? Remember that? Please remember this because it's very, very important. If I asked you to do this, step 1 would be to try to take the antiderivative. And let's say we don't have a calculator. Okay? Well, right now, you don't know how to do that. By the end of this unit, you will be able to take the antiderivative. But for right now, you don't know how to take the antiderivative of that. We know that it's not going to be x squared over 1/3 x cubed plus x. That's not how antiderivative rules work. You can't just take the antiderivative of the top and the antiderivative of the bottom. It's not going to work. Okay? So, I don't know. Here's a situation. I want to know the exact area under F from 0 to 9. But all I have is a bunch of points on F. At 0, at 2, at 3, at 7, and 9. So, will I be able to find the exact area? No. Will I be able to find the exact area for this right now? No. That's what you can do, and what we're going to talk about all class today is approximate the area. Now think about it for a second. Here's a random function. Could you give me a numerical answer for an approximation of the area under this function? Go ahead and talk about it with your neighbors really quick. Give me the number. If you say yes, give me a number. I'll give you a number. 5? 5 looks good. How do I get 5?
You can do it like basically how to do it in physics. You can pretend like it's almost like impulse, like you do a triangle.
Yeah, why don't we use shapes? Now, I don't know exactly what this value is, so I'm going to actually make it easier. I'm just going to use a rectangle here. I'll use a rectangle here and a rectangle here, and I'll say like, oh, I'm a little bit over here, but I'm also a little bit over on the other side here. This is 2 by 4, that's 8. This is 2 by 2, that's -4. This is a 1 by 1, that's 1. 5. I'm going to use shapes. I'm going to use shapes, I'm going to use geometry. That makes sense? Now, I'm using 3 shapes. What could I do to get a better approximation? One thing I could do is use maybe lines that go onto my curve a little bit better. Sure, that's one way. What would be another way to get a better approximation? Could do that. That's kind of like using the lines. Other ideas? I use more shapes. Use maybe a rectangle here, maybe a rectangle here, rectangle here. Wouldn't this give me a better kind of understanding of what's going on if I use more shapes? Okay, good. So that's something that we're going to keep in mind. Like more shapes, better approximation. Okay? Cool. Well, the process of using shapes to find approximations of areas is called a Riemann sum. Okay, it's a process where we are going to use a specific type of shape depending on the type of Riemann sum. We'll use that shape to approximate an area. There are 4 types we will focus on: a left, right, a midpoint, and a trapezoid. The left, right, and midpoint all use rectangles. The trapezoid uses a trapezoid. But the rectangles are going to be different, and we're not going to just throw rectangles down willy-nilly like we did on the previous question, or the previous situation. We are going to be very specific and formulaic based on the type of Riemann sum. Okay, so the first one is a left Riemann sum, and we are going to approximate the area under this function, which we don't know the shape of, but at least we know some points. The left Riemann sum uses rectangles. Where the heights are determined by the function value over the leftmost point of your base. Okay? Now, we got a point at 0, 2, 3, 7, 9. What we're going to do is going to say, you know what? Our rectangles are going to use those x values as our bases. So my first rectangle is going to have a base from 0 to 2. I like to indicate it on my table. And if I have a graph, I can indicate it on my graph. My first one is from 0 to 2. Now for a left Riemann sum, with this being my first base, I'm not going to use just a random height that's like splitting the difference between 1 and 3. Instead, I'm going to say, use the point all the way to the left of my base. So like all the way to the left of my base, use this value. So I'm going to use this value as the height of my first rectangle. And I can see that area is 2. So my area is going to be approximately, my first one is a base length of 2, a height of 1. The second one, 2 to 3. 2 to 3, I'm going to use a height of 3. So that's 3. Base length of 1, height of 3. The next one from 3 to 7, I'm going to use the height of negative 2. So from 3 all to 7, I'm going to use the height all the way over to the left. There's this height. This is a base length of 4, a height of negative 2. This is negative 8. And then from 7 to 9, I'm going to use the height of 5. So I end up using this 1, this 3, this negative 2, and this 5, and I exclude the 4. Okay? I like what Mr. Foreman's doing here. He's saying use this one to the left. I like that. Okay? So 7 to 9, ignore the 4, use the 5. This is going to be 10. This is going to be 2, base length of 2, height of 5. You can add these up, 7. Okay? Is that going to be an accurate approximation? I don't know, but it's just a left Riemann sum approximation. Okay? All right. Right Riemann sum approximation. Same deal as the left, only the height is on the right of your interval. Height over or under the right most point. of your interval. So, first 2 points, 0 to 2, that's going to be my first base. But instead of using 1, I'm going to use the point all the way over here at 2, which is 3. Using that guy. So now my first approximation is going to be 6. Second one from 2 to 3, I'm going to use this height to the right, -2. That's going to be -2. 3 to 7, height of 5. It's 20. And 7 to 9, my height's going to be 4. That's 2 times 4, that's 8. So I got 12 plus 20, 32. 2 times 3 plus 1 times -2 plus 4 times 5 plus 2 times 4, which is 32. Okay. Midpoint. Now, I was supposed to put in more information, but I didn't, so please include this information. 1 is between 0 and 2. Let's say the height ends up being at 2. 2.5 between 2 and 3. Let's say the height's actually at 3. 5, which is between 3 and 7. Height's 0. And 8, which is between 7 and 9. The height is actually 6. So I now have more points. I get this point 1, 2. I get this point 2.5, 3. I got the point 5, 0. And I got the point 8, 6. Okay, so we know a little bit more about what our function looks like. You know, maybe it looks like this. Don't assume it looks like this, though. Don't assume anything when you're just given points. We know that things do not necessarily connect in a nice, smooth way where this is a max and this is a min. You can obviously go underneath values. You can go over values. You do not necessarily have max and min values. But why I needed those points there is because if I use my same bases, like from 0 to 2, the midpoint Riemann sum uses the function value over the middle of your interval. So instead of using 1 or 3, you use 2. Instead of 2 and 3, you'll use the function value over 2.5. Instead of 3 or 7, you'll use the function value over 5. Instead of 7, 9, you'll use the 1 over 8. Okay? So here the height is not determined by like an average. The height of your rectangles is determined by the value over the middle of your interval. Okay, so to draw those from 0 to 2 using the height of 2. That's 4. From 2 to 3, I'm going to use the height over 2.5. Just so happens to also be 3. That's cool. From 3 to 7, my height is 0. That's just going to be a rectangle of 0. And then from 7 to 9, my height is 6. I got 4, I got 3, I got 0, and I got 12. 2 times 2, 3 times 1, 4 times 0, 6 times 2. So 19. Cool. All right, to the trickiest one, the trapezoidal Riemann sum. Now I'm going to draw 2, but the other 2 that deal with this negative value, I'm not going to draw because it might not make sense. Here's the trapezoid that we're going to draw. starting from 0 going to 2. We're going to take our 2 points and connect them with a straight line, and we will bring down lines to our bases. Question? Oh. Here, from here to here, here, here. There's another trapezoid. Those are the easiest ones to kind of visualize and see. Okay? Now, many of you are probably thinking, okay, find the rectangle of area and then add the triangle. Yes, and this is what you've done up until now. But there's actually a formula that we can use to make this a little bit easier to calculate in case we have to do many of them. First, let's remind ourselves of what trapezoids look like. You are typically familiar with a trapezoid that looks like that. Our trapezoids look like this. Nope. Almost good. Let's see if this works. Just keep missing. There you go. Our trapezoids look like that. But they both are trapezoids. Now, does anybody remember the area formula of a trapezoid from geometry back when you guys were freshmen, or some of you 8th graders? No, it'd be like a midpoint formula. Close. Close. 1/2 our height times the sum of our bases. Where this is base 1, this is base 2, or vice versa, and this is our height. All right, well, now our trapezoids look like this. What is the visualization of H if our trapezoid's on its side? Yeah, it's the width. What used to be the height is now, I think I answered the question. The height is now the base. And then here, the bases turned out to be what's on these? Our heights. You see that? This is the formula we can use in the future if we have a triangle on top of a rectangle, is instead of doing like 2 separate area calculations, for this first one, the area is 1/2, my width is 2, my heights are 1 and 3. And look how easy it is to get that answer is 4. Let's do the last one. I'll do it in blue. 1/2. The width was also 2. The heights are 5 and 4. That's 9. Now for the other ones that are going to be kind of weird to draw, they end up kind of including some triangles. Like if I connected this from here to here, but it goes through, if it connects like that, it's like, it ends up being kind of like 2 triangles. But how do you find the area of that? Don't worry. Like, don't worry about the picture. Worry about the formula. So from 2 to 3, let's do this in like purple or something. From 2 to 3, the base length is 1, the heights are 3 and -2. Just use that. Okay? So from 2 to 3, 1/2 base length of 1, heights of 2 and 3. So this is 5/2. Okay? So don't draw them if you're ever having negatives and you're not sure what they look like. And then from 3 to 7, I'll do this one in green. From 3 to 7, don't draw it. It might be confusing. Just use the formula. Base length is 4. The heights are 2 and 5. Sorry, -2 and 5. And why did I say 3 and -2? This should have been -2. I'm sorry about that. I was wrong here. This is 1/2. If you guys were just like watching, you would have caught that. Depends on if you're watching or if you're zoning out and watching. All right, this is 2 times, this is 3, so this is 6. Okay, so don't draw them if they don't end up looking like trapezoids or if they go over. If you just use the formula, this is the trapezoidal Riemann sum. Okay, fantastic. Now, we still can't find this exact area because you don't know the antiderivative, but we can approximate this. Any ideas? What should we do to approximate this? Yes, split it up. Let's use a table. Now, we're going from 0 to 3. So that means my table, if I'm looking at some points, should be from 0 to 3. Now, if you want to do a lot of math, you can split this up into like a bunch of different intervals. You can go from 0 to 1/2, and 1/2 to 1, 1 to 1.5, 1.5 to 2, 2 to 2.5, 2.5 to 3. But that's going to take a while, and that's really going to actually use a calculator to do the calculations. We don't have a calculator. Let's pretend we don't have a calculator, because if we had a calculator, you would just type into the calculator. And what your calculator actually does is a very advanced Riemann sum to give you a good area approximation. Okay, your calculator doesn't know antiderivatives, but it does do lots of quick calculations. But some values that are easy to work with maybe are the whole numbers. Maybe we're going to make all the widths going to be to be the same. We'll plug in values. 0 over 0 plus 1 is 0. 2 over 1 plus 1 is 1. 4 over 5. 6 over 10. That's 3/5. Okay? And then, I don't know, like, let's do a right Riemann sum. With as many subintervals as we can. I would go 0 to 1. Which height do I use? 1. 1 to 2. Use the height on the right, 4. 2 to 3. Use the height on the right, 3.5. What's nice is that since they all have the same base, you can actually factor out the base and just add up the heights. It's not going to be something we'll do that often because most of our intervals are actually going to be different. So you can either do this calculation or factor out the 1, just add these. So 7/5 plus 5/5 is 12/5. Why did I pick a right Riemann sum? I don't know. Who cares? Doesn't matter. It's just one of the ways to approximate the area under that curve. Now, what we are going to do is not only be able to approximate the area, but if we know certain characteristics of our function, we can say whether or not our area is over or under the actual. We are going to examine a right Riemann sum, a left Riemann sum, and a trapezoidal Riemann sum. Let me do this in different colors. That way it's very clear. I'll do right Riemann sum in black, left Riemann sum in red, and a trapezoidal Riemann sum in blue. Okay, now these are 3 different functions, but they all have one defining characteristics. F prime is positive. Since f prime is positive, what is consistent at all 3 of those functions? What? No. Increasing. And when you guys told me you're just going to watch and just be able to answer, we should be able to just like quickly answer that. If a derivative is positive, the original function is increasing. Okay, right Riemann sum. Over or under for the first one? Over. I know it's over for a fact. Now, how do I know? Maybe split this into 2 intervals. What is going to be the function value you use? The one all the way to the right, right? Well, that area is definitely over the actual area underneath it. So the right Riemann sum, over. Now, it turns out you don't have to use 2. You could just use 1. from A to B, if I use a rectangle over the rightmost point, the right Riemann sum stays over regardless of the concavity. This is not something that you're going to memorize in the future. This is something that you can understand and visualize. If your function is increasing, concavity does not matter. Your approximation's going to be over. Please write a little note to yourself to the right of this saying concavity does not matter. Now, will left Riemann sums be over? Will they be consistent in their answers? You guys discuss that with your neighbors so that you do some thinking today. The left is definitely under for all three of these. If you use the leftmost point of an increasing function, the leftmost point is the least value, so these are going to be under, regardless of concavity. Now, left Riemann sum, right Riemann sum, consistent for increasing functions. Trapezoidal Riemann sums, will it be consistent? Find out whether you are over or under or something else for all three of these. Go. Well, I don't want to say consistent. I want to say over, under, or...
Exact.
Yes, there you go. Exact for the first one, with no concavity, a trapezoid's right on the money. Over for the second one, because it's concave up, a straight line ends up over the concave up increasing curve. And then here, under, because of the concave down curve, this is under. Now, are you going to memorize these? No, you're not going to memorize these. And I'm just doing this for increasing functions. If I asked you over or under, just like I did with over and under approximations, and with approximations, concavity mattered. So tangent line approximations, you remember we draw a curve with a concavity. Didn't matter if it was increasing or decreasing, it was all about concavity. These are over approximations. That's how we told ourselves whether our tangent line approximation was over or under. For this, we're going to draw our curve with our characteristics. Here, we got positive f of x's and derivatives that are negative. What does that tell me? F is doing what? Decreasing. I don't know how it's decreasing. It could be like this. It could be like this. It could be like that. But it's decreasing. The question is our left Riemann sum over or under? You guys should be able to answer that and discuss it with your neighbors really quickly. It's not memorizing things. It's not looking at your notes. It's not looking back at what you just did and what you just wrote, because if you look back at your notes, you're going to get it wrong. Regardless of concavity, if you're using a left Riemann sum, the function value over the leftmost point ends up being the highest value. And in this case, a left Riemann sum is over. So this is how we're going to do these in the future. Draw pictures and just understand what's going on. If it was right, it'd be under. It is not easier said than done. You can do it. It's easy to do. Yes, you can. Your brain can't draw things, but your fingers can. What if it's trapezoidal? I would not ask you this question, Mr. Hotmeyer, with this information and ask you, is a trapezoidal Riemann sum over or under? What would I have to include in this statement? The concavity, Mr. Foreman. Very, very good. I'd have to tell you how it was decreasing. I'd have to tell you it's decreasing like this, or it's decreasing like this, because a trapezoidal would be under in this situation, a trapezoidal would be over in that situation. Okay? All right. Fantastic. More shapes. Better approximations, right? Now, When we talk about shapes, we like to talk about a term called a subinterval. You will see this term a lot when you're answering questions on your homework. When we get into the free response questions, subinterval is really the amount of shapes. And typically when we talk about subintervals, we refer to the width. Now the width of the subinterval is very easy. Talk about the range, the overall range. If you're going from 0 to 3, the overall range is 3. Divided by the number of shapes. I'm going to use n for number of shapes. So if I want 3 shapes from 0 to 3, the width is 1. 6 shapes from 0 to 3, it would make sense that the width is a half. Okay? Now, we're going to keep this in mind for kind of conceptual purposes. Another thing you could call this, all of our widths for all of these situations end up where? On my x-axis, right? All of those widths are on my x-axis. So I'm going to call this b minus a over n delta x. Okay, that's the width of my subinterval being an amount of shapes. All right. What we've been doing is we've been summing up a bunch of these heights times these widths. Now, the stuff on the left is not super important, but we actually say it's an x sub I to give it a specific starting point. We say it's I starts at 1 to make it a right Riemann sum, rather than I starts at 0 to make it a left Riemann sum. That's not important. And it goes to n, where n is the number of shapes. Remember, delta x is b minus a over n. Okay. If more shapes become better approximations, and if I continue to add more and more shapes, my approximation gets better and better and better. How many shapes should we use for you to feel like we have such a good approximation that we are approaching the actual, or we get the actual value? Throw a number out with your neighbors. It's not enough.
100.
100's getting there. Infinity. Okay? If more shapes become better in approximations, 7 shapes would give you a good approximation. 100, better. 1,000,000, a better approximation. Infinite amount of shapes, exact area, right? I don't want it. Yeah? Oh, man.
Show you this. Because I want to be. So
it needs to. It's not as of right now. As of a certain point at a 3-week mark. We can't talk about this right now. Teach in class. Okay. Better and better approximations. What would we do? We would want infinite shapes. Okay? Now, we can't take this formula and just plug in infinity. We don't like to plug in infinity for numbers. It's more of a concept. We like to say things can approach infinity rather than equal infinity. So what do I use when I talk about things approaching certain things rather than equaling things? Limits. Ew. Now guess what, guys? The integral that we've been using, that you thought came from just like a notation for an antiderivative? It's kind of a chicken egg situation, but turns out the origins of the integral were from here. This is an infinite sum. It's a sum of an infinite amount of things, okay? And mathematicians are like, I don't want to write this all the time. This takes too long. So they decided to use a very skinny s for sum. This is actually the origin of the integral. The origin of the integral was to represent area under a curve represented by an infinite sum. Now, what are we missing? The a and the b, right, for area? Well, that came from this width of a subinterval, a to b. That's the b minus a part of the delta x. Where did f of x come from? Well, f of x stayed here. But now what are we missing? I have an integral. What is usually next to this f of x that you're familiar with? The dx. And you have thought of the dx as what? With respect to x, or just something that Mr. Messner tells us I have to write down, but I don't know why. Is that mostly the case? Yes. Okay. Well, here's what it actually is. Again, we are taking an infinite sum of heights times widths, right? These are rectangles. This is the area formula of a rectangle. These are my heights. What happens if n approaches infinity here? It gets very, very, very small. We've talked about delta x as like an overall change in x. Right? What have we used in the past for an instant change in x? A small, small change in x. Remember, delta y over delta x. What's this stand for? Slope. What kind of slope? Secant slope, right? What is this? Change in y over change in x. Instantaneous change in y, instantaneous change in x. This is my tangent slope. Well, this dx actually represents a very, very skinny width. What we have been doing, using the fundamental theorem of calculus and using antiderivatives, is actually doing an infinite sum of an infinite amount of rectangles with infinitely skinny widths. And your calculator does this type of process. This is blowing some people's minds. I know. Don't worry about it. Once you get to your homework, you're just going to be doing a bunch of error. Your calculator does this process. Your calculator takes a whole bunch of rectangles and adds them together really quickly with very, very skinny widths. What you do, because you can't do that, is you use the fundamental theorem of calculus. You take the antiderivative, you do change in position, you do ending position minus starting position, rather than doing an infinite sum. This is backwards from how I thought it in the past. I used to introduce this first and then introduce the antiderivative. I think students will understand not much of it regardless. So, what I'm telling you, and this will help us in the future, what does this mean? This means take the antiderivative, right? It also means it's an infinite sum. What does this mean? This means take the antiderivative of f with respect to x. It also means an infinite sum of heights times skinny widths. They are equivalent. They are the same. This is why calculus gets confusing in the second half, is the fact that there are multiple things, multiple representations of the same thing. Anyways, what's important for you guys? The following. Having a table of information and being able to find the Riemann sum. I'm not going to spend time doing this because it's just practice, okay? This is more like just practice. Okay? Having a table of information, finding a Riemann sum. But don't forget certain things. Let's go to this last example. Okay? One of these, you can find the exact value for. One of them you can't. Using this table of information. You should remember that your first attempt to find an exact value is to take the antiderivative and find the change. Now, for h prime, I can take the antiderivative, and I can find h of 6 minus h of 0. But h's antiderivative is big H. Do I have big H anywhere? No. Can't do that, so I'm going to have to use a Riemann sum. Now, what you're going to be asked to do on your homework is approximate values like this. Not big H, regular H. Write this down. And they'll say, approximate this using a left Riemann sum with intervals, subintervals indicated by the data. And then it says, interpret what you find. What would be the interpretation of this? Is it the average rate of change of H? This is just the average H. 1 over b minus a, integral from a to b of whatever you're trying to find the average of. That's average. Now, you're going to have to do the work to approximate this. You're going to have to do, 0 to 2, 3, 2 to 5, 2, 5 to 6, 5. So that's 6. This is 6. Wait. Yeah, that's 6. This is 6. This is 6. This is 5. 6, 6, and 5 is 17. Your average H is going to be 17 over 6, found using a left Riemann sum approximation. You're going to have to be given V, use a Riemann sum to approximate this, and interpret that. So there's a lot of review. What would be the interpretation of this once you found it? The answer is 17 using a left Riemann sum. What's the interpretation of that if this is V, and that's V? Not distance. Displacement, especially because this V is negative, this is displacement. Do you remember that? From unit 7? Do you remember this? What's that? What would you have to change if these are your V values and you have the absolute value of V? This negative one needs to be a positive one. Okay? These are all kind of examples of what you're going to see in your homework. We might as well start your homework because we have some time. All right, let's go to this first free response question. We'll go straight to B. And what they're missing is one extra statement, which is an interpretation. Okay. You have to use your calculator to do this calculation, but it asks you to use the trapezoidal sum from 0 to 0.3, 0.3 to 1.7, and 1.7 to 2.8 to approximate the value of the integral from 0 to 2.8 of v of pt, and then to interpret it. Let's first talk about the interpretation. What would be the integral of v? Come on, everybody needs to know this. This is Unit 7. Displacement. This is the change in position. Okay. Now, what I think is like the unimportant that you have to be able to get, the easy part, is doing the work. 1/2 base length, 0 to 0.3, the base length is 0.3, times your heights. That'd be your first trapezoid. Plus 1/2 your base length times your heights. Plus 1/2 your base length times your heights. That's it. The actual calculations aren't tricky if you just remember them. What's tricky is usually the interpretation and the use of it. I do a good job in your notes of questions. So 1/2 3, this is 0 plus 55. This is 1/2 1.4 from 55 and negative 29. The last one is 0.9. That's the base length, negative 29 and 55. Cool?
Wait, where are you getting these decimals?
Where am I getting the decimals from? Sorry, it's not 0.9, it's 1.1. Where am I getting the decimals from, Mr. Hotmeyer? The base length, 0 to 0.3, that's the base length. These are my heights. 0.3 to 1.7, the base length is 1.4. Does that make sense? All right, let's go up. Approximate an integral from 0 to 4 of x squared using a trapezoidal sum with 4 subintervals and using a midpoint sum with 2 intervals. What do we need to approximate something like that? Mr. Gerard, you answered this earlier. Can you answer it again? What do I need to approximate this? A table, points, 0, 1, 2, 3, 4. F of x would be 0, 1, 4, 9, 16. 4 subintervals, 4 shapes, 0 to 1, 1 to 2, 2 to 3, 3 to 4. Midpoint sum, 2 shapes. Your shape would be from 0 to 2, and then 2 to 4. All things you just need to be careful of. Make sure you do your homework. Be ready for interpretations, etc., etc. Thank you.